We're going to start a little bit early if that's okay. A couple of minutes ahead. We just have such a big schedule and so much to do and so many people to talk. If it's okay with you, we'll get started early.
All right.
Okay? So first of all, welcome to the 2014 Cold Fusion Colloquium at MIT. And we've got 3 days. We've got incredible people coming. The whole reason that this field has flourished is because of the people who are speaking here and the people like you who've come. So I want to thank you. You really are fantastic. I'm only going to give the first part, why cold fusion is important, because we don't have enough time. And also I want to apologize. I spent so much time getting this together, I didn't cut back my slides. So if you feel I'm dousing you with too much slides later, I apologize in advance. The reason we need cold fusion is energy. The reason is we don't have enough. And cold fusion is clearly the light at the end of the tunnel. And there's 3 reasons why. When we burn deuterons to make helium-4, we have abundance, we have safety, it's pollution-free, and we have a humongous energy density. Abundant, water's everywhere. 1 in 6,500 hydrogens is heavy hydrogen, and we can burn it in cold fusion to make helium-4. There's no radioactive pollutants, unlike the rest. And in fact, if we look at the energy density of cold fusion, we're out here. Not quite the theoretical limit. Explosives are over here. So we know we're far beyond the chemical energy that we're burning. Notice that some foods like donuts that we're going to be giving you later have a higher energy density than dynamite and TNT. And the reason they're safe is there's a very slow release of energy in your body. But it is interesting that it comes out higher than that. Finally, if we look at the energy density and the power density compared to most energy production sources, cold fusion is way out on the right. This is really important for us to consider. And so let's do a little consideration of your coffee. Your coffee has approximately, I went through some numbers here. If you have 55 cc's of water, we've got about 3 molars of hydrogen. We therefore have 940 micromoles of deuterium as opposed to 514 micromoles of caffeine. The caffeine will keep you mentally active for 5 hours. If we burn the deuterium to helium-4 with an efficiency of 10%, at 1 watt, we find we can make an equivalent battery that lasts 18 years from a cup of coffee. And that's not even pure heavy water, that's ordinary water. And if we're able to burn it to helium even faster, for example, let's suppose we're going to have a talk on car airplanes. Suppose we were actually able to take our cold fusion equipment and use that as something we were going to drive. The car presently takes 80,000 watts of power. If we were driving it at 100,000 watts for some safety and some other stuff, we'd get 2 hours flight. So when you drink your cup of coffee, the caffeine here will keep you elevated for 3 hours, but it could actually keep you in a car elevated for 2 hours. Okay, so let's start. Our first talk is Arik El-Boher, and he began studying mechanical engineering and metallurgy in Israel. Oh, I'm sorry. Before we start, Peter, please.
2 thoughts. The first thought is we don't have a microphone. For those of you who speak softly, that's not me. When you speak, you have to really belt it out. The other thing is that organizing a meeting takes an insane amount of work. I don't know why anybody would put in that amount of time. It's just outrageous. In this particular case, I was very busy, so I really did anything. But I wanted to draw attention to all of the time that Mitchell put in. I really appreciate the time and effort that you put in. You guys might also. We're going to thank you again at the end as well.
is a beautiful field learner is a big part of this. It's I just do the scholastic stuff. When you're sitting actually drinking the coffee and powering your planes. Thank Hale. You want to say more?
No.
Okay. Arik studied mechanical engineering in Israel at the Ben Gurion University in Beersheba. And then they were very lucky to get him at the University of Missouri for the Skinner Project, where he's been doing metallurgy. I think when we start successfully applying cold fusion to commercialization, it's going to be metallurgy and mechanical engineering is where it begins. So we begin with his talk.
Thank you. Good morning. The title is very ambitious, and I just want to give you to say something. Although it's called, the title is Progress Towards Understanding of Anomalous Heat Effect, and the reason we put anomalous heat effect is really because we don't know yet, whether it's nuclear or not or something else. In all our experiments since 2002, we never measured gammas, neutrons, so I want to keep it as anomalous heat effect with your permission. But we made a lot of progress, and I'm going to tell you a little bit about this progress. I think that we see some light at the end of the tunnel, and I hope it's not a train coming. As Mitchell just mentioned, we started in 2002 at Energetics with being very ambitious, trying to commercialize LANR, cold fusion, or whatever, anomaly heat effect. But we were very objective, and we came in 2009 to the supporter, the financial supporter of the company, and we said that deserves a much deeper research, and there was a decision after 60 minutes to move the whole project to the University of Missouri. And in fact, the group of Israelis moved to Missouri and later on absorbed in the university, and now the company is not active. Now the goal, the mission, the directive of Skinner, which stands for Sidney Kimmel Institute for Nuclear Renaissance, is to find what is the mechanism. And to try to do it, we have another 3 years to do it. We are fully financed and qualified to do it back in the University of Missouri. And we hope we will be successful. We cannot promise. And of course, all the data and all the results and all the information will be publicly open. And we are inviting groups to collaborate with us. I will talk about those issues, about the structure of Skinner, and then some results and the initiatives and what are known up till now, what progress we have been made, and what are the future experimental programs or experiments that we are suggesting to do, and I will finish with some conclusions. So this is a chronological time scale of all the groups that we are collaborating with. As you know, in 1989, ENEA and SRI started just after the announcement. I think Mike McCoubrey was involved even before. And 2002, Energetics started being active in this field, later on was supported by DARPA, and SRI and NRL were collaborating with us to replicate our results, which were very successful. And as I said, after 60 minutes, we moved to Missouri. Energetics ceased to be active, And we, in the last 2 years, TSEM, it's the company which is now organizing the next ICCF 19 in Padua next year in May, and coalescence and re-research, and just lately aerospace. We are collaborating with all those groups in order to improve the reproducibility and to reveal the mechanism which is responsible to this unbelievable amounts of heat that we saw, and we believe that it's true. Now in Skinner, this is the stuff that we are working, but at the same time we are collaborating with a group of 7 groups in the university, and we are very lucky to collaborate with those groups. Professor Gal and Gagor Padiai, Kaiser, Katy Katesh, Kowalski, Perlas, and Professor Pfeiffer, each of them in a different field. And as you all know, it's a multidisciplinary kind of research, and we need all of them. John Gall is working on cyclotron bombarding targets at high energies, and also on exploding wires together with SRI. Shubra is collaborating with us on nanostructures, which are essential to this field. Professor Kaiser in the reactor of the university is running the Newton scattering, and we are in the process of running experiments in C2, that is loading by electrochemically, gas loading and plasma loading, and at the same time measuring the lattice parameter and see what happens to the lattice while it is being loaded and converted from alpha to alpha plus beta to beta phase. And I think this is a very essential thing to do. Kowalski is running plasma cells bombardment at low energies. Mark Perlas is working on gas loading, mainly with titanium sponges, and Peter Pfeiffer on high gas loadings. Now, for those who have not been in ICCF 18, few pictures shortly to give you some idea about what we have back in Skinner. And actually, all the equipment you will see is actually moved as a gift from energetics to the university. So this is the plasma and gas lab in which we have gas loading cells. This is, by the way, the cell in which we are replicating Francesco Celani experiment with wires, Constantan wires. On the other side, those are gas plasma bombarding energy cells with mass flow calorimetry. This is the lab for preparation of foils. There are roll mills, annealing furnaces, treatment, metallurgical furnaces, glow discharge etching, spot welding, and so on and so forth, all the equipment which is needed for preparation of cathodes. This is one of the labs in which we are conducting ultrasound experiments inside incubators to keep the temperature stable and constant, with all the equipment around it, with temperature stabilization, water buses, and so on and so forth. These are the closed cells, and in one of those incubators we'll put a bar of palladium. We are going to run an experiment of 1 year shortly. We got the bar, the pure palladium bar, from Professor Bebirian, and these are closed cells, helium-tight closed cells, so we'll be able to extract samples, gas samples, to detect if we will see, in case of excess heat or not, helium-4. And this is the last lab of open cells isoparabolic calorimeters. We have here 9 cells in temperature controlled buses, and we are running a lot of experiments in this lab, and all the best results we got was in this lab, 64 and others that you will see later. Now, the collaboration is such that all the groups are working according to the same standards, with the same cells, with the same protocols. We are sharing everything, cathodes and operating procedures. And all those groups will be conducting hundreds of experiments of different cathodes and different configurations, again in order to improve reproducibility and to try to understand the mechanism which is responsible for this amount of ecstasy. Now, some statistics. This table, large table, is an accumulation of experimental data from the year 2002 up to 2009, just before we moved to University of Missouri. There are several experiments, almost 1,000 experiments, from which about 20% were successful and generated ecstasy. I will talk during my talk about storm. What is storm? Storm suggested years ago to have cathode made of platinum and anode made of palladium, and so that by electrolytic process you will get co-deposition of palladium on the platinum. At the same time you are loading the precipitated palladium, and actually you are getting loading and coating in situ, and all those experiments produced ecstasy, 100%. It's not a huge number of experiments, but sufficient to show that something is going on. Although the ecstasy was at the range of 5 to 10%, but happened every time. So we will use this method later on. You will see in the presentation to detect nuclear emissions. Then we will. These are all kinds of cathodes, and the most successful were palladium with zirconia and palladium with carbon nanotubes and rhenium, palladium with carbon nanotubes, as it here, palladium with rhenium, and these are, and with lanthanum, and these are the cathodes that now we are concentrated towards our effort to understand the mechanism. This is a distribution of all the experiments, but now on the x-axis we have the amount of power gain that we got. And you can see, obviously, that most of them lying in the low end of percentage, and 64, for example, is here. And since 64, which was tremendous amount of heat released, we couldn't replicate it, but lately we got very interesting results, which I'll show later. Now, this is 64. I will not go into it because many of you saw it so many times. What I want to mention is that, as you can see, we started with a system which was absolutely balanced, and suddenly, after a few hours, these are seconds, and these are powers in watts. There was a burst, very erratic, which was went on for 17 hours and stopped by itself. So what we have done, this is why we called it 64A, and there was the second episode, 64B. We deload and load again, and we got again ecstasy. Now, what I want to mention here, that the most interesting thing is that as the exercise started, the voltage in the electrochemical cell gradually increased from 3 volts to up to 15 volts. Now, this we saw in any of our exercise events. Something is going on inside the cell, probably due to an increase of capacitance, probably if the double layer on the vicinity of the cathode. And also, what I want you to pay attention is that everything becomes very erratic. You see, it was very, very nice, smooth, and suddenly, when there is exercise, everything becomes to be erratic. And we were studying that. We were measuring RF emissions. We'll talk about that later. And we believe that it has to be with resonance on the cathode. These are the temperature distribution of the same experiment. You see that there is a full correlation with all the temperature, independent temperature elements. The power is extracted from T4 and T5, but these are for indication, and all of them are in full agreement. Even the bus, which is a 40-liter bus, was elevated in its temperature due to the burst of heat which was released from the cell. Also, you can see these 1, T1, and 2, and 3 are inside the cell. So you can see absolutely that the heat is coming from the center to the radially out, and there is no doubt that something is going on at the center of the cell. Now again, this is the voltage. You see, it started from 3.5 volts and it went up to 15 volts. Very erratic, and this is most important parameter. Just to give you some indication about the energies, so this experiment showed excess energy of 1 megajoule, and the next one even higher. This is the second episode. We had also boiling, and when I'm talking about 4.5 megajoule that you will see immediately of excess energy, I'm not counting the boiling which took place inside the cell. And again, the voltage increased and was very erratic. Temperatures were up to boiling, and actually we were boiling more than 250 milliliters of D2O. And you know, after 60 minutes, Garvin said that he wants to see boiling a cup of tea. So you can actually boil a cup of tea here. And again, the voltage, as you can see, is gradually increased and very erratic. And these are the energies, 4.5 megajoules. This is the input energy, and this is the output energy, and the red is the excess energy. And because the input energy is so small, EX, or the energy, the excess energy, is close to the output energy. Huge amounts of heat, not taking into account the boiling amount of energy, just the sensitivity. Now we thought that this is due to these spots, black spots we call them, carbon spots, which are the electric, and as a result, when you are applying the electrochemical process, actually you are creating a very strong electric fields which are creating increase of temperature locally close to these sites. So we were trying to get those spots artificially. We were not so successful. Just to give you some indication of what does it mean, a black spot. This is a carbon, and we are spotting this point. And you can see that most of it is carbon and some other ingredients, but that didn't bring us to a good reproducibility. Another peculiarity, look, this is the platinum wire which is connected in order to measure the resistance, 4 wires measuring the resistance on the cathode, and another wire for delivering the current. Look what happened to the platinum. Usually it's smooth, and the temperatures were so high on the cathode that the Teflon, which is insulating the wires, were burnt off along 2-3 centimeters close to the cathode. People were claiming maybe your current was so high that, and you didn't know about that. If this is true, and if you calculate the resistance of the wires, the platinum wires, as compared to the cathode, the whole wire with its insulation was supposed to burn off, but it wasn't. It was just close to the cathode. And look what defects due to the temperature. And actually, if you will look closely with SEM, you will see spots of palladium. So there was migration of palladium from the cathode to the platinum wire, close to the cathode. So tremendous amount of heat was released. Then we thought that maybe the grain size has to do with it. So we conducted a very substantial set of experiments, changing the grain size by changing the annealing protocols of the cathode. And we couldn't. You can see that the blue curves are those which didn't produce excess heat. The red, those who produce excess heat. But they have exactly the same grain size. This is the grain size distribution. So that also did give us an answer. But we know that by annealing, we are releasing stresses, we are making the process of loading of deuterium or hydrogen into the lattice easier, and it's easier to get to high loading ratio. So it's important to get high loadings, but it's not promising high reproducibility rate. So then, as you know, crystal orientation and specific contaminants are very important, and I'll speak about that a little bit later. But we looked for some kind of figure of merit in order to identify or to quantify the quality of the surface, the morphology of the surface. So we have selected the power spectral density function, which is basically a scanning of the surface with atomic force microscopy, and then analyze it with Fourier transform analysis, and to come up with a figure of merits which are giving us some quantitative results on the morphology of the surface. We had an intuition that the morphology is important, and I think we were right. So what happened, we took 64, which is the leading cathode, which was cut into so many pieces and have been spread all over, NRL, SRI, ENEA, and others, to try to understand what was going on. And as you can see, these are the boundary layers, the grain boundaries, but you see a labyrinth structure. And when we analyzed the surface, we saw this is 1 over the wavelengths, or 1 over micron, and this is the x. We came to the conclusion that the x-axis, the y-axis is the higher the amplitude, the higher the probability for excessive. And the fact that we saw these 2 peaks, you will see them in many other surfaces that we have analyzed. It's a good indication for getting higher reproducibility and getting excessive. So the previous one was just a one-dimensional, or I would say one-dimensional scanning with the atomic force microscope, line after line. And the second one is 2-dimensional. If the surface is homogeneous and uniform, the morphology is uniform, then you don't need to do it 2-dimensional. But in principle, you see the same results. And here, this is a cathode which was produced by ENEA, and in order to come as close as possible to 64. So what they have done, they have doped the palladium with platinum and then etch it, and as you see this labyrinth structure, and you see these two peaks. Although lower than 64, but still this experiment generated excess heat of 25 to 30%. And the more we went in this direction, the better we saw that this parameter actually helps us to screen the cathodes and to know which cathodes are more likely to produce excess heat. And again, this is another one with another experiment from 2013 made at LANR, and you can see again 40% and 30% and so on. And that direction is very promising. The second direction that we are working is with glow discharge etching. Instead of chemical etching of the surface, we are exposing it to a bombardment of ions. We can make it with any gases, but if you will see with deuterium, the reproducibility rate is higher. And this is how the surface looks like. And actually, after rolling, you get orientation 100. And 100, since it's an FCC, you get pyramids with square base. So this is what we see. And actually, all those pyramids are actually recrystallization of the palladium after being liquefied and evaporated due to the bombardment of ions. And here you can see the scale. So it's quite big chunks of palladium and very modified surface, which increase the probability for getting excess heat. Now, we continued, as I said, smoothly in Skinner, in Columbia, in the incubator, and then in Skinner. And this is one of the experiments that, by the way, people are rushing. They are running experiments for 1 week. If they don't get excess heat, they leave it. This experiment was run for 40 days. If we were running it for 1 week, we couldn't see anything. And so, no excess heat. Actually, even, you see, the calibration was that even P out was lower than P in. So we had what is called negative COP. And it was with this C until this moment where we moved to superwave. And after a few hours after moving to superwave, suddenly you saw the burst and all the temperature increased, and we got excess power or excess power gain of 70%, and we had few of such experiments. And this is what happened on the lattice. Beside the fact that you have this labyrinth surface, you see these cavities. Those are negative crystals. Actually, a pyramid was evaporated from the surface, and we called it negative crystal. And the same in another experiment, which gave about 100%. Then we moved, also in Israel, and continuation in Skinner, to ultrasound excitation. Just to put it in one word, the surface, the lattice, the surface are important, but also you need to apply dynamics to the system. If you will work with DC, it will hardly happen. But if you are applying dynamics to the system by the superwave, by ultrasound excitation, shocks of cavitations, as I'll show you immediately, you improve the probability to get excess heat. Also, these cavitations are developing the surface to be the surface which is needed for excess heat to happen, but there are many other ingredients which I'll show immediately. So definitely from 20 from 20%, we increased to the reproducibility to 40%, and it's not minor. Now, as I told you, we are using superwave, and we are using two types of application of those ultrasound excitations. A ring of a transducer, ultrasound transducer, which is emitting the waves radially towards the focus in which the cathode is located, the palladium cathode, or by 4 tabular transducers, which are same thing, focused at the center of the cell where the cathode is installed. And this is the arrangement, these are the anodes, so that the wave will not be interfered as it is approaching the cathode. And that in some lots we got up to 70% reproducibility, and this is some of the results. You can see here 75%, 80%, and in average 74%, but there were a lot of failures which reduced from other lots, which reduced these nice numbers of reproducibility. What is important when you are using ultrasound excitation, and especially ultrasound excitation with power level which creates cavitation? Cavitation, collapse of bubble, jets of deuterium impinging the cathode and actually deforming the cathode and actually creating dislocations, creating defects, creating deep traps within the bulk of the cathode, and that allow to increase the absorptivity of deuterium into the cathode. So, first of all, ultrasound is cleaning the cathode, and you know that electrochemical processes are introducing a lot of contaminants on the cathode. So ultrasound is cleaning and making the cathode more active and ready to get the excitation and to start the process. Second thing, by using this method, the duration of generation of exocet is much longer than in regular electrochemical cells. And last but not least, and we'll see it immediately, the deloading, the natural deloading of deuterium from the lattice is much lower than any electrochemical other cell, and we believe is due to the formation on the surface of the cathode due to this plastic deformation. But if you will look on these, here we have up to 3,000% exocet. Here we have 200 and 500 and 600, and the durations are days, 23 days, 12 days, and so on. Very long processes, much longer than in any electrochemical regular cell which is not excited by ultrasound. So dynamics is important, and this is how the surface looks like. You remember the labyrinth structure or labyrinth surface? It's actually a pitted surface, like millions of hammers hitting the surface and creating these funny shapes, gliding shapes, gliding surfaces due to the stresses developed in the lattice while being loaded. And in fact, we are able to load into a very high loadings with super waves, but with very low current densities, unlike other electrochemical processes. I'm talking about less than 6 milliamps per square centimeter, getting all the way to close to unity. Also, we see craters, all kinds of craters spread on the surface, and there is no doubt that melting took place. You can see it even visually. Oh, I'm sorry. as you can see here. But as you will see shortly, we analyze it with SEM and EDX, and we saw that here in the rims of the craters, there was an increase of concentration of platinum. Now, in any electrochemical cell in which you have palladium as cathode and platinum as anode, there will be ions of platinum precipitating on the cathode. So this is not nothing special. But around the rims, we found 15% of platinum, which means, according to the phase diagram of palladium platinum, that melting took place. Now, melting is 1500 degrees centigrade about, and this is immersed in a solution. So you can imagine what was the temperature in these craters. So we thought that this is the source of heat. So in order to find some correlation, you need to scan the whole surface step by step and to find some figures of merit. The problem is that it's a very costly process to scan a few centimeters long cathode. Will take 28 hours, and it's not cheap, and it's almost impossible. So I will be glad to, if someone has this ability and he has a SEM automatically scan, to send them, and that we have to identify algorithm to identify these craters and to number them and to see the sizes. And we know the amount of heat which was released from each crater, so we can make calculation, very easily calculation, if this explains the huge amounts of heat. We suspect not, because we saw those craters also in systems which didn't generate excess heat. And negative crystals, as we saw, and slip bands, and so on, and these labyrinth structures that you already saw the behavior. Now, this is our ultrasound experiment which generated excess heat, and again you see the two peaks, and when the profile looks like this, there is no chance that we'll get excess heat. NRL got into the picture, as you saw on the chronological scale of time, and they were conducting 120 experiments with 0 results. By the way, one of the reasons they were running experiments of 1 week. So sometimes it's too short to see what's going on. So in order to accelerate the process, they start adding by injection NiSO4 and other ingredients into the solution, into the electrolyte. Why they did it? They believed that it would precipitate on the surface and create this morphology. And in fact, they analyzed it after that, and they saw this typical morphology, and they start seeing excess heat. Now you can say, well, it's chemical because they had some stuff which was reacting with the electrolyte, but no, the amount of heat, it is much, much greater than any known chemical reaction. As you can see, they got 10 kilojoules for 90 minutes at 140% power gain. This is another experiment, and this is how the surface looks like. Very, again, with deep grooves around the grains, and these are the precipitation of the material, which is making it, again, as a very developed labyrinth type surface, which increase the probability for excess heat. Now, this is one of the experiments that we just got lately with carbon nanotubes, and basically we are talking about palladium overplated with palladium as an adhesion layer, and then the carbon nanotubes and another layer of palladium or rhenium or lanthanum or all kinds of those materials that you saw in the statistics slide. Now, these are hours. So after about 400 hours that nothing happened, it started. And as you can see here, this is P in, Pi net, and P out. Now, Pi net is a reduction of the heat of the power of dissociation of the electrolyte. And so we are subtracting it since it's an open cell. But it doesn't matter. Even if you take P in, total, I times V, without subtraction at all, you see that the input power, whether it's Pi net or P in, is much, much smaller than P out. And these are the amounts of heat released. Actually, at peak, 55 times more power out than power in. And then it stopped by itself, and after 20 hours, it started again. But this time, this was overnight. This time we were in the lab. So immediately what we wanted to see is if we are measuring rightly the voltage, because the current, you have to open the circuit. We didn't want to open the circuit. The moment we touched the poles, the voltage dropped. And as you can see, where is the voltage? I don't see it now, but the voltage went up to 12 volts. And as we touched it, immediately the voltage collapsed back to 2.7 volts, which is the typical voltage when there is no excess heat. Now, what we believe happened is we had this resonance that I'm talking about, and that built a capacitance inside the cell, and the moment we touch the poles, we collapsed. The impedance was changed back to the initial conditions. This is why we believe that resonance is very important, and we have to excite the lattice at high frequencies, and that will increase the probability for excess heat. This is how the surface looks like. Actually, this is the palladium upper layer. Remember, we are talking about a sandwich. And this is the cathode. And after at different scales, you see a cauliflower. It's like a fractals of cauliflowers. And when we analyzed the surface, the morphology of the surface with atomic force microscopy and Fourier analysis, we see again the two peaks, and that increased the probability to get excess heat. These are all the experiments that we are running up to right now in Skinner. Celani's replication, we are still going on. I'm sorry to say, but we didn't see yet excess heat with this system. Electrochemical cells, we are using also solution with the suspended nanoparticles which are being precipitated while being loaded in electrochemical cells. These are giving us excess heat, and the morphology that I talked about, carbon nanotubes, artificially structures of PT cathodes to get the morphology under control. This is what we are trying to do. And we are also starting experiments with magnetic fields. We believe that part of this, getting this resonance effect is by using magnetic fields combined with ultrasound excitation and so on. I will not go over all of it, but many of those experiments I already mentioned before. What we know so far from new data we got we believe that what is important is that we are getting an inductive resonance. You remember this capacitance that I talked about? Unstable voltage, unstable voltage and resistance ratio measurements, everything is very erratic when we are getting excessive. Surface contaminants like platinum, silicon, aluminum, and so on. RF emissions in all the laboratories, in ENEA and in NRL and others, when we measure excessive, we measure RF emissions at high frequencies from megahertz to gigahertz region level. We are talking about acoustic, it's important, acoustic triggering, and we never saw activation of the material. That's why we call it anomaly heat effect. Maybe few people will be annoyed, but this is what we found, and this is why we don't know what is the source or the mechanism which is responsible for these huge amounts of heat. Now we also know that it's important to have orientation of 100 on the cathode, because that helps to get high loading. Labyrinth morphology, peaks in power, spectral density correlation with the appearance of excessive, as I showed, voltage increase, high loading, sharp increase in temperature coefficient of resistance of PD cathodes, and again, no neutrons, no gamma that we have found. Now these are experiments that we are suggesting, and actually some of them we are actually running. You remember the storm experiment in which the cathode was platinum, the anode was palladium, and there was a co-deposition of palladium on the platinum, and with these experiments we saw ecstasy. Now, small ecstasy, but if it is from nuclear effect, if we'll put here an X-ray detector or gamma detector or another detector to measure charged particles, or neutron detector, we will be able to see if this is a nuclear source or not. So what do we have? We have a silicon nitride membrane which is less than half a micron thick. On the other side we have a electrochemical cell, as we know, anode, and the membrane is the cathode. We are plating the cathode, the silicon nitride, with platinum, and the anode is made of palladium. So we have a co-deposition. We thought about that due to all these people which were working in this direction: Bokris, Boss, and Gordon, and Cravens, and Letts, and Swartz, and Legata in Padua, Italy. So far, although we are running those experiments, we didn't see any X-ray emissions. But we are continuing. We will do the same thing with magnetic fields, with permanent magnets as well as electromagnets. And this is how it looks. As I said, either it's a PT anode with an electrolyte, which is like palladium sulfate dissolved in the solution in order to build a layer of palladium in situ on the membrane. This is the membrane, the silicon nitride membrane, and the detector is here. Or, as I said, replace the order and put the anode as the palladium and the platinum as the cathode, and get the deposition of palladium in situ. Now, what that gives us, as I said, all our calorimeters have sensitivity of 1 to 10 milliwatts. That's fine, but that's maybe not enough. So by introducing this method of putting here the detector, let's say the X-ray detector, so in the membrane experiment we see 1 keV X-ray, which is a amplification of 10 to the power of 12 as compared to the thermal calorimeter. So we are actually sensing femtowatts, much more sensitive. But even with this sensitivity, we didn't see yet any nuclear emissions, any X-ray emissions. Is it nuclear? I don't know. These are the list of experiments that we are conducting, and I spoke about that. This is a summary of the best experiments that we got. You can see here 64 and A and B. And the most interesting thing is that people were talking, I think, Mitchell, that you showed this slide in which the level of energy or the specific energy that you get is higher than food but lower than nuclear. So let me tell you that these two numbers are, at least this one, is creating 70 watt per gram of palladium. Now any nuclear reactor, fission reactor, can generate heat according to the figure of merit of 20 to 50 watt per gram uranium. So we are in a better situation. And of course, these are the percentages: 25 times, 50 times, 30 times, and now, as you saw, even 50 times power gain, as in our experiments. And these are the summary of our collaborators. All of them are generating excess heat, and I think we are in the right direction. So just to conclude, you know that we are getting palladium for all kinds of sources, and sometimes even from the same source we get different properties of palladium, and this is a problem. This is a control problem, metallurgical. Some of the components, some of the cathodes, some of the raw materials that we are getting working better than others simply because they have some contaminants that are helping in the electric field generated on the surface of the cathode, generating phonons, creating resonance, and preparing the cathode for starting the process of generating excess heat. So this is important and has to be analyzed carefully before starting experiments. So the addition of controlled inclusions on the lattice strongly affect both the formation of the initial structure or the morphology. We saw this labyrinth structure, and the phase composition of the material, and the mechanism of PT deuterium loading, and later on the generation of excess heat. You remember the carbon, the black spots, the carbon spots, which are generating electric field, but not only these, some other materials are doing the same thing, and creating a high electric fields between the non-conductive and the conductive phases on the surface of the matrix, and those are highly important. And if nuclear or any other reaction takes place, it must be on these sites. As we talked about the ultrasound, in exposure of palladium cathode to ultrasound, we get longer duration of excess heat, higher reproducibility, surface which is a labyrinth type morphology. All those things increase the probability for excess heat. Also, as maybe I'm just finishing. Oh, here. You see, this is loaded cathode, which was exposed to ultrasound excitation. It takes 120 days, and still it's in beta phase. While if you take a regular electrochemical cathode, which was in electrochemical process, from the moment you disassemble it to the moment you bring it to the X-ray diffraction instrument, it's already at 40% loading, and it takes really it's very fast, goes to alpha phase and actually to fully deloading. So something, the ultrasound, the formation of the surface, the creation of deep traps is holding the deuterium or the hydrogen inside the cathode, and this is also improving the probability to get excess heat. Okay, this is more or less, and this is a progress, but this is not still a breakthrough, but I believe that we are in the right direction to get control of this very complex phenomena. Thank you.
Questions?
Thank you for a wonderful summary of remarkable work. You talk about resonance. It can be solely electrical, electrochemical, electromechanical, various combinations. Now, if I heard you right, you're talking about an inductance that is an electrical resonance. Do you have a candidate for what causes that inductance?
We are now conducting, I didn't speak about that because of, I had to shorten my my presentation, but we are conducting electrochemical spectroscopy. And in order to understand exactly this, and Orchidea Zizi, our electrochemist, this is what she's doing and this is what she's focusing on in order to understand what is causing these electroresonance on the surface.
Okay, so, but you don't have any idea what might be causing the inductance yet?
No, but we believe that you may help it by inducting, by exciting it from the outside to resonate the cathode. So think about it.
Yes.
Yeah, this was excellent. Stan Spock, a long time ago, wrote some papers about 15, 18 years ago, looking at that interfacial layer. Mel Miles has since looked at it and concluded that what you're doing when you have codep going is producing what amounts to a supercapacitor. And this is in keeping with a lot of the things that you're observing here as well. So you've got a very complex structure. Now, is your person doing cyclophotometry to measure that as you load the cell up?
No, but we will glad to collaborate with you on that.
Have you have a lot of chemistry going on in your system. For example, you have the carbon. But whenever I ask...
I'm sorry, you have?
You had carbon.
Yes.
Whenever I ask people where it came from, they say it came from...
No, we know where it came from. First of all, there are two sources of... go ahead.
No, it's okay.
Sorry.
So I would like to suggest that you can have nuclear reactions that have transmutations of the heavier nuclei, and that would explain a lot of the excess heat. That's my suggestion.
You ask what's the source of carbon? There are two. One is from rolling. When you are rolling, you are lubricating the rollers, and we know after annealing, you are actually creating these black spots, the carbons, on the surface. This is one source. The second is the carbon nanotubes that we are working with. It is. It isn't.
Does that account for all of it, or could there be nuclear transmutation?
I don't.
That my suggestion is it won't account for it. That's all. I don't need to be too aggressive.
Yes, Peter.
The question is,
Sorry.
what ultrasonic frequencies have you used, and what weird stuff are you doing?
Yeah. We are working in the range of 20 to 30 kilohertz. Now it's not. This is too low frequency. I believe we need to be in the gigahertz, terahertz zone. But I believe that these, even those are hammering, at low frequencies are generating higher frequencies, which may raise to these levels of frequencies. Yes, please.
When you do your cavitation excitation, are you including the energy you need to produce the cavitation?
This is a very good question. The answer is no. From two reasons. First, the transducers are, as you saw in the picture, they are external transducers. They are far from the cathode, and we are consuming a lot of energy. We are intending to submerge transducer, miniature transducer, just close to the cathode, and with that, we will be able to save 90% of the power. But even at that power, what is happening is that how we are exciting the process. We are introducing excitation together with electrochemical process, together for 24 hours continuously. And then we stop, we see the improvement in loading. Then we apply it again. And we apply it in a time span of about a week between each excitation. And after 4 or 5 such episodes, when the system stabilizes, only then the exercise starts. So you can say, whoa, so you haven't stored energy. We looked at it, we cannot find a mechanism of storing this energy. And mechanical storage is orders of magnitude lower than the amount of energy that we got. So the answer to your question is no, we didn't take it into account. Secondly, it's supposed to be down the road much, much lower than it is now. And in any way, it is not continuously, but it is in terminations being applied. And then you let it run for 40 days.
Question over there.
Congratulations, thank you for talking. I'm an RF guy and a fractal guy. And I've been here an hour and I'm already excited. The results you're showing so far seem to imply there's importance to the roughness of the surface on the cathode, and that there are resonances in a variety of ways that you're seeing. I just want to point out, as a point of information, that fractal surfaces, rough surfaces, have very interesting specters of resonances. And what you're seeing, I'm going to predict, and you even told us, I'm going to tell you what I think you should be seeing. You should be seeing, for the RF excess, you should be seeing a tremendous number of multi-band emissions at the lower frequencies, and a very broadband, almost continuous range of RF coming at the higher frequencies. Those are characteristic of rough fractal surfaces. And if that's the case, then it becomes interesting to then be able to characterize those surfaces with a fractal dimension, something called lacunarity, and so on. So I'm going to be quiet now, but I just wanted to point out there are other ways of characterizing the surfaces that may help you hone in on which ones are the best ones to try to go.
Thank you for your comment, and let's discuss it later. Thank
Larry.
you.
Yeah, there's one other thing, when you do the ultrasound, Ken Sussman, University of Illinois, did a lot of work in sonochemistry. So at that interface where you were doing this, you're going to have very high temperatures. You're going to be breaking up all of the electrolyte and reforming it on the surface. You're going to have an incredibly active chemical surface there. So you may very well end up with, if you, for example, if you've got lithium in the electrolyte, these are going to not only interpolate in, they're going to drive in further, making more complex species. I suspect that that has a lot to do with what's happening in terms of the absorption and also removing the reverse path, the desorption. And a lot of this is also related to what Stringham has been doing, where he claims that he's got essentially injection of deuterons in there. So you've got a couple processes going that normally are not available in electrolysis.
I agree.